In Chapter 20, we're going to introduce inductance. And to do that, we're going to talk about Faraday and Lenz's law, which is probably the coolest things that we're going to talk about all semester, but probably one of the more difficult things to get your heads wrapped around. So this was invented by Michael Faraday. He lived in England back in the late 1700s, 1800s, and he was a great experimental scientist. And so he discovered a lot of what we call electromagnetism. And after he gave a demonstration of what we're going to see here in a minute, somebody came up and said, so what use could this be? And I find that ironic because it's basically makes our modern electrical life possible. That is one of the most useful inventions ever made. So when we're doing basic science as scientists and somebody asks us, so what good is this? Well, you just never know. That basically we don't know where science is going to take us, what use it's going to be. We need to discover. So what is this experiment? Well, we're going to talk about transformers eventually, but it's basically the basis for what makes a transformer work. And the idea is called induction. So here the one experiment is to wrap wires around an iron core. And the iron core, since it's magnetizable, it's ferrite, it's iron, then it can pass the magnetic field. But it only passes the magnetic field when that magnetic field is changing. So that idea of a changing magnetic field is going to be key for us moving forward. So the current can be produced wirelessly from one coil to another by this changing magnetic field. And it's only produced right after the switch is open or right after the switch is closed. So only in that initial burst of energy when that magnetic field is changing is this possible. And so that's why eventually we're going to talk about alternating current, which makes these devices really, really useful. Another way to do the experiment, which is one we can do just in the classroom a little bit easier, and you can see the effect, is just put a magnet inside a coil. So here in the animation you see somebody just taking a magnet in and out of a coil of wire, and as that magnet is moving, we see the meter registering. But when the magnet is stationary or not there at all, then there is no reading. So the idea is that we need to have this magnet moving in the coil to create this current, to create this voltage that we're measuring. So the idea is that we need a change in magnetic flux. And so the two examples we've seen before are one, we're changing the current. Two, we're changing the strength of the magnetic field, and two, we're moving the magnet back and forth, so we're changing the strength of the magnetic field. But we can also change the area of the magnetic field, which is where this idea of the flux is the amount of magnetic field that were captured in an area. So magnetic flux is defined very much like electronic flux is it's the field. So before we talked about E, when we did Gauss's law, but now here we're going to talk about B for magnetic flux times the area. And so this looks very similar to Gauss's law, but we're going to use the magnetic field instead, because we can change either B or A and get the magnetic flux to change. And it's such an important concept that it has its own units of Weber. So magnetic flux is, again, could be an area. So if we have something rotating in a magnetic field, it will change the magnetic flux. So if I have a loop and we have all the magnetic field lines going through, then we have a maximum amount of magnetic flux. But if I turn this loop, we have no magnetic flux whatsoever. So what happens? So we need now an equation. Is that we're putting the change in magnetic flux over time is what creates an EMF. And this is what is Faraday's law. Is that if I have a changing magnetic flux in a loop, so that's what the ends mean, is that this is typically done in a loop, then I will create current. And this is exactly how generators work, which we'll get into some next time. So what is Faraday's law of induction? Is basically that if we have a change in magnetic flux, then it is going to create an EMF. And this animation shows that as I'm changing the area, we are then creating an EMF, a source of electricity. So In this example, we're going to look at this loop as it's moving to the right. Now the loop itself is not changing area, but the area exposed to the magnetic field is. So the magnetic flux does change. So we start out with Faraday's law, recognizing that magnetic flux is my magnetic field times our area. And there is a sign in there, but everything's perpendicular, so we're not going to worry about that. And we say it's just one loop. So here we say n is equal to 1, and we're going to expand our flux to an A and a B term, and over delta T. Here the magnetic field is constant, so this isn't changing. So I'm going to pull that out. And so I just have B constant. I'm looking at what's changing. So this is the slope then of this curve is delta A over delta T. So I can calculate the flux at each different time period. So we say that the magnetic field is 2 Tesla. That's my B. So I have 2.0 Teslas times my change in area. And the problem says it has a maximum area of 0.1. So it goes from 0 to 0.1. Remember, deltas are always, delta A is always A final minus A initial. So the area in the magnetic field is the total area finally, so 0.1 minus 0, and 2 minus 0 meters squared and seconds. Then this gives us negative 0.1 volts. And you can see it is negative here. And this negative sign is what we're going to talk about coming up. Basically, how do we understand what positive and what negative means? Now it's physics, so we can understand that that's going to be a direction. But how do we tell what direction that is? Now in this area, the slope is 0, right? Slope equals 0. So I get 0.1 minus 0.1, I can't write, times 4 minus 2 seconds is 0, because 0.1 minus 0.1 is just 0. So there's no voltage when the when the loop is in the magnetic field. Now see if you can figure out what E is. This is going in and exiting. So see if you can see what the EMF is on exit. Okay, so hopefully you're up for that challenge. So we get negative 2.0 Teslas, and now we're doing 0 minus 0.1 over 6 minus 4 seconds. And that also gives us 0.1 volts, but positive. We switch the polarity as we're exiting that magnetic field. Here's all those values nicely written up in case you couldn't read my writing on the last line.